Hey everyone, I'm Nick, and in this episode of From Scratch, we're going to be looking at writing a matrix multiplication kernel in CUDA, but using cache tiling using shared memory, which is a very common optimization used by many kernels. Right? So let's go ahead and move to that directory, cache tiling, and we'll create a new file called matrixmul.cu. Right? So we'll be doing matrix multiplication. Right? So this program computes matrix multiplication on the GPU using shared memory, right? So shared memory is really just a user managed L1 cache. So if we directly know what memory that we want to use, right, we can preload it into shared memory, and then every time we access it, instead of having to go to main memory and hoping that we hit in a cache, it'll be guaranteed to be in shared memory because we put it there. So unlike a normal cache, it doesn't get evicted, right? So shared memory is also sometimes called scratchpad memory. Okay, so so then we'll also say who it's by, right? So we'll say by Nick from coffee before art. And as usual, we'll do a couple things, right? So we'll write our boilerplate code, right? So we'll go ahead and outline our main function and then this global void matrix mul kernel, right? And we'll fill in both of these, as we kind of go along. So the first thing we need to do is, just like with all of our examples, we need to set a problem size, right? If we're computing something, right? So set the matrix dimensions, right? So we'll be doing a square matrix, right? And we'll just go ahead and do the same that we did last time, which is going to be 1024 by 1024, right? So we'll say default is equal to 2 to the 10, right? So it'll be 2 to the 10 by 2 to the 10 matrix. So we'll say int n is equal to 1 shifted over 10 times, which is the same thing as 2 to the 10. And then we'll also say, we'll calculate this bytes here, right? And we're just doing this so that later on, when we're allocating memory, we don't have to do a calculation. We can just go ahead and say we're allocating bytes of memory. And this bytes will be n times the size of an integer, right? And so if we want to do floating point or double precision matrix multiplication, we would just have to change the size of int to be size of float or size of double. Okay, so the next thing we need to do is allocate some memory, right? So allocate memory for our matrices, right? In order to do that, we'll first create some pointers, right? So we'll have int a pointer a, and then we'll have a pointer b, and then a pointer c, right? And we'll just be using square matrices. If we wanted to do more generalized matrix multiplication, we would have 3 dimensions, right? So we'd have m, n, and k. So we'd have an m by n matrix times an n by k matrix, which would give us an m by k result, right? But that's just a more general form of square matrix multiplication. Okay, so now we'll go ahead and allocate space, right? So we can do it 2 ways. We can use CUDA malloc or CUDA malloc managed. If we use CUDA malloc, we have to explicitly do copies. If we use CUDA malloc managed, as soon as we access some data from a pointer on the GPU or the CPU, that memory will automatically start transferring over to either side, depending on where we access it. So we can avoid some mem copies. We can go ahead and just use CUDA malloc managed. Right, and we'll pass in the address of these pointers, right? So this and bytes, and then we'll go ahead and do this for all 3 of our matrices, right? So we'll need space for A, B, and C, right? And the same size for each. An n by n matrix times an n by n matrix will give you an n by n result, right? Okay, so the next thing that we have to do here is we need to go ahead and initialize our A and B matrix. So we'll have init our input matrices, and we can just do this with a little function up here. So initializes a square matrix with random numbers. Okay, so we'll call this, it'll be a void function, right? And we'll call it init matrix. And it will just take 2 things, right? So it'll take a integer pointer, right? So the pointer to one of our matrices, right? And we can just call this m, and then the dimension, right? And if this was a non-square matrix, we'd have to pass in 2 dimensions, or we'd have to pass in, say, the total number of elements that we want to initialize. And we'll also go ahead and include C standard lib, right, for some okay random numbers. They're not great random numbers, but we don't really care about the randomness that much in this case. We just need to fill it with something. That way we have something to test against. Fill the matrices, that is. Okay, so here we'll just use a for loop. So for int I is equal to 0, I is less than n times n, I plus plus, right? So for every single element in our square matrix, we'll just set this im of I equal to rand, and we'll just do mod 100. So this will give us random numbers between 0 and 99 inclusive. Okay, so now we actually need to call this function from our main. So we'll go ahead and call init matrix twice, once on A within elements, and then we'll call it on B as well, right? And we don't need to call it on C because C is just going to be it's just going to store the output, right? We would initialize C to say 0 if we didn't want to have a temporary variable inside of our kernel, right? If we didn't have a temporary variable inside of our kernel, or if we initialized our C matrix to 0, we could just store the partial result directly into that C matrix. Otherwise, we just accumulate in a temp, and then we just clobber over whatever is currently sitting in that spot in the C matrix. So the next thing we'll do is we'll go ahead and set up our grid dimensions and our block dimensions, right? So this will be the grid of threads, or the grid of thread blocks, each of the thread blocks being a smaller grid of threads that we're going to lay over a problem, right? So we'll have, so we'll say set our CTA and grid sizes. So we'll have this int threads is equal to 16, and we'll just use this because we'll be working with a 16 by 16 thread block. So each thread block will actually have 256 threads. Alternatively, we could say have a 32 by 32 thread block, and that would be 1024 threads per thread block. In this case, we'll just use 16 by 16 though. The next thing we'll do is we'll have our grid dimension, right? So fundamentally, we want one thread block, right? Or each thread will go ahead and compute one output element, right? So we'll launch as many threads as we have elements, okay? So in order to do that, we have to figure out, how many threads need to cover each dimension. In this case, it's a pretty simple problem because it's a square matrix, so the number of threads we need to cover the x dimension is the same number of threads we need to cover the y dimension. So in this case, we'll use that trick that we've used in the other videos as far as padding goes, and we can just do in plus threads minus 1 over threads, right? So in this case, for this input size, we don't need the padding because 1024 is evenly divisible by 16, so we'd be absolutely fine just doing normal division there. But in any cases where we don't have an input matrix size that's evenly divisible by 16, we would need this padding here. Okay, and then the next thing we need to do is go ahead and set up our structs that actually get passed in as kernel arguments, right? So these structs are they're called dim3. They basically have 3 dimensions, right? So it'll have an x, a y, and a z dimension, and this corresponds to we'll have one of these for our thread blocks, right? Because our thread blocks can have an x and y and z dimension of threads, and then our grid itself can have an x and y and z dimension of thread blocks, right? So we'll go ahead and just say threads, and then we'll use a constructor, right? And we'll pass in threads, comma, threads here, and then we'll have a dim3 of blocks, and this will be, actually, let's call this blocks instead, right? Because this is how many blocks we need in each dimension. And this will be of size blocks by blocks, right? And so these are equivalent to saying, blocks dot x is equal to blocks, right? So using this constructor, it's just positional. So this is the x dimension, this is the y dimension, and then we're leaving the z dimension as being, default, right? Which in this case, for both of these, is going to be 1, right? Okay, so that's it as far as setting up our So what have we done? We've allocated memory for our matrices. We've initialized our matrices. We've gone ahead and set up our launch parameters. The only thing that's left to do is to launch our kernel. Right, so we'll go ahead and call matrix mul. Right, we'll use this triple angle bracket notation, and we'll launch blocks, threads, close this out, and then whatever our input arguments are going to be. And then because we're not using explicit CUDA mem copies, we have to make sure we synchronize after a kernel launch, because kernel launches are asynchronous. So we'll use CUDA device synchronize, which just makes sure that all the previous jobs sent to the GPU have finished by the time we get past this synchronize point. Okay, and we'll go ahead and say launch our kernel. Okay, so the next thing we need to do is to start filling out our kernel, right? So first of all, what are we actually going to pass in? Well, clearly we're going to pass in a couple pointers, right? So in pointer A, B, and C, which will be our input A and B matrices and our output C matrix. And then we also need the dimension of our matrix, which will be in because it's square. If it wasn't square, we need to pass in M, N, and K. Okay, so now we've got that. So let's go ahead and change it down at our call side as well. We'll pass in A, B, C, and N, right? Uh-oh, that is the synchronize. So move back up here to our kernel launch, right? A, B, C, and N. Okay. So now we can start talking about, what are we actually going to do in our kernel, right? So the first thing we need to do, or the first thing that we're going to do, is we're going to talk about shared memory, right? So shared memory is something just like global memory we have to allocate. And there's two different ways we can do this. We can do it dynamically, which means that at runtime we decide how much shared memory we're going to allocate, or we could have it pre-decided at compile time, which means the compiler has to know how much shared memory we're going to use. Oftentimes, static allocation of shared memory is just kind of easier to deal with, because we can just directly insert the values or the size of shared memory we want inside of our kernel, but that's not always possible because there's situations where you don't know how much shared memory you're going to need until runtime, so you'd use dynamic allocation. In this example, no, the amount of shared memory we have will be a function of or it'll be something that we know a priori or ahead of time. So we'll just go ahead and define it up here. So for every thread block, what we'll basically do, the difference in the two implementations of matrix multiplication, the simple one last week, or not last week, in the last video, and this one today, is that in the last video, every single thread just marched along main memory, computing, basically the product of two elements, and then accumulating it into a partial result, right? This time we're going to be doing something a little bit differently. What we're going to be doing is that same operation, but in 16 element chunks, which is basically the dimensions of our thread blocks, right? So each thread block will basically compute chunks of 16 elements of matrix multiplication at a time. And what we're basically exploiting here is the fact that we know exactly what memory we're going to access next. So what we'll do is we'll load in 16 chunks into shared memory, and then when all the threads are accessing those chunks, instead of having to go out to main memory and hope they get lucky in the cache hierarchy, instead they can guarantee that will be fast shared memory, which is at kind of the L1 level, so it'll be very, very fast. So in this way we get some we can get some great performance speedups by not having to have long latency memory operations, right? We can guarantee that it'll be very quick because it's in shared memory. Right, so in order to do this, right, so because we're working with shared memory in the size of thread blocks, or the shared memory is going to be sized based on our thread blocks, we'll go ahead and have just a define up here, so a compiler kind of macro up here, and we'll say that shmem size stands for shared memory size, and we'll just have this be 16 times 16 times 4. So this will be this will be computed by the compiler and just inserted everywhere we put shmem size. And this is how we do statically allocated shared memory, because the compiler knows how much we need. Right, so here inside of our kernel, we'll say allocate shared memory, right? And what we'll go ahead and do is we will have this little kind of prefix that says shared, and we'll have an integer array, and we'll call this A, And how many elements do we need? We actually don't need this for because we're not allocating bytes. It's elements in this array. So we can just pass in shmim size, right? And we'll do this for A and B, uppercase that is. And this will hold our little individual matrices. Now it's important to note that shared memory is private per thread block. So other thread blocks can't access the shared memory even if they're going to use these same elements. They'll have to load in these. They'll have to load in those values themselves. Okay, so this is basically how we allocate static shared memory, or statically allocate shared memory. So the next thing that we'll do is just like we did in our other example, which is we'll calculate our global row and our global column. Right. So here we'll calculate our global, or each thread's global row and column. Right, so to do this, it's that simple calculation. So for the row, it'll be block id x.y times block dim.y plus thread id x.y. Right, and just as a reminder or refresher of how this works, so rows are in the y dimension, right? So that's why we're using the dot y's. The block id x times block dim x says, okay, for this particular threads, first we figure out how many blocks down this is in our grid that we've defined, and then the thread id x.y says, what's our offset in the y dimension for those blocks, right? Or within that block, right? So this gives us our kind of base, and then this gives us our offset, right? And we'll do the exact same thing for the column, but this time columns are in the x dimension, right? So this will just change to, instead of .x, it'll be .y. Okay, so there's a good start. The next thing that we need to do is we'll have a loop, right? Except this time our loop is going to be a little bit different. In our original matrix multiplication example, our loop was based around, whether or not, we were actually going to, our loop was going to be based around whether or not we were actually going to, or iterating over the entire matrix, right? So we would just do a loop across in elements, and we would compute the product of the A and B matrix and store it into temp. This time it's a little bit different because we're going to be basically moving a chunk or a tile, right, which is the size of our thread blocks, 16 by 16. We're going to be loading in 16 by 16 elements into a small matrix, doing matrix multiplication on these small matrices, and then moving the tile over, right? So moving it over for the A matrix and then moving it down on the B matrix, right? So our calculation is going to be a little bit different, right? So move the tile across the length of the grid, right? So we need to move the tile over as many spaces as based upon the dimension of the tile. So in this case, we need to move a 16 by 16 tile, enough to cover n elements. So we'll need n over 16 movements, and we'd need to pad that if it's not evenly divisible, right? So in order to simplify things, we'll go ahead and so we'll extract some built-in values to simplify code, right? So just so we don't have to write thread.idx.x and thread.idx.y and calculated dimension every single time, we'll just kind of extract those into temporary variables. So we'll call tx equal to thread idx.x. We'll call ty, or ty will be thread idx.y, and then we'll have an int dim equal to block dim.x. Now this could be block dim.x or block dim.y. It's a symmetrical thread block, so both of those will be 16, right? So we just choose whichever one of them, right? And this is just so we can simplify our code, so we don't have to write out these long things every single time. Okay, so let's go ahead and move our tile across, right? So we'll do for int I is equal to 0, I is less than, this time we have to do a quick calculation, which is just going to be n divided by dim, right? So if we have an n by n matrix, right, to move the tile across n elements, right, it'll be n divided by 16. So in this case, you could just do n divided by dim, or if you wanted to pad it, you would have to do in plus dim minus 1 over dim, right? And then here you would just do I plus plus, right? And then you would have your for loop, right? So this is a padded for loop. Okay, the next thing we need to do is, now that we have a loop that moves our tile across, we actually need to load the elements into that tile, which means we need to load it into these 16 by 16 arrays, right? Stored in shared memory. So how do we do that, right? So in order, we access them just like arrays, which means we store and load from them just like arrays, or just like accessing memory. So to do that, we'll go ahead and load into A first. So this is the matrix that we're going to be moving across, right? And this will just do ty times dim plus tx, right? So every single thread inside of a thread block, right, we'll go ahead and load one element, right? So what are we actually going to load? So we'll load based upon the position we are inside of our big global matrix, right? So when we're moving across the A matrix, our what's going to happen is the first thing is our row is going to be constant, right? Because you know, if a thread starts out at row 0, going across the A matrix the entire time, it'll be along row 0. So we can go ahead and calculate that, and that will just be it'll be whatever the row currently is times in, right? And so that's it for the row calculation. So what's going to change every time we move this tile over is going to be it's going to be the column, right? So in order to calculate which column we're at, right, the first thing we need to figure out is how far has our tile moved, right? And that will just be a function of I times dim, right? So every single time we move the tile over dim elements, right? And then the other thing we have is inside of this tile, where are we, you know, inside of this thread block, right? So we'll just be at tx, right? So the column will be tx because we're moving over in the x direction, right? So just as kind of recap of this, row times in gives us, you know, which row we belong to that we're going to be traveling across. I times dim says which step of the tile moving we're at. And then tx says, you know, within this step, which thread am I, right? Or which column am I going to access? Okay, all right, so this will load 256 elements into our 256 element piece of shared memory. And again, this is shared memory per thread block. This is private per thread block. Okay, all right, so that's loading into A. So the next thing we need to do is load into B. Now B is a little bit different. Each thread is only going to load one element, right? And it'll be the exact same, it'll be positional, right? So where a thread is in the matrix, it'll just load whatever elements in that spot. So, and then multiple other elements will end up using that in their calculations. So what will we do here, right? So we'll load from B this time. Now what's going to change is, you know, this time the row is not going to remain constant because we're going to be moving down rows every single time the tile moves, right? So the first thing we need to calculate is where are we based upon the current iteration of this loop, right? And so this will we'll start out by doing I times n, right? So whatever iteration of the loop we're at, that's where we're going to, you know, kind of the base of this tile, right? So the next thing we need to do is we need to figure out where we are within the thread block, right? So now we're going down the y dimension of the thread block. So what row is each thread on, right? And so that will be ty times n, right? And then this time the column's going to stay the same, right? And so that will end up being plus column, right? So the column stays the same for these threads. Oops. And we need to go ahead and comment that, right? So let's kind of recap this one now. These calculations can be kind of tricky if you're not used to working in 2 dimensions and kind of thinking spatially. So we'll go over B again. So right, so this first calculation is I times n, which basically says, where is my tile at in the y dimension, right? So every iteration, the tile moves down, or sorry, this isn't I, it'll be I times dim times n. There we go. Sorry about that. Okay, so every iteration it'll say, okay, if I'm on the 0th iteration, we'll start with a base offset with a base of 0. And the first iteration will move down I times dim, which will be 1 times 16. So it'll move down 16 rows. So every single iteration, the tile will move down 16 more elements, right, in the Y direction, which means we need to go across 16 times in elements. Okay, then ty times in says, okay, for each thread in the Y dimension, we need to multiply that by in, right, because each element in the Y direction is separated by in elements. So if we're right here at 0, between 1 in the Y dimension, there's in elements we have to go across in the X direction before we loop back around to get to the second element in the Y direction. And then the column, like I said, that remains constant because we're just moving down that the entire time. Okay, a little bit tricky, but after we do that, it's okay. Okay, so the next thing we need to do is after we load from shared memory, we'll go ahead and call this __ sync threads, right? And this just basically sets a barrier saying I need to make sure that every single thread gets to this point before we can continue, right? So it says, okay, every single element will synchronize here. So A will be populated and B will be populated. So warps may be going at different speeds. Warps are just collections of 32 threads that make up the thread blocks. The programmer doesn't actually program warps or do things with warps. We think mainly on the granularity of thread blocks that get scheduled. But some thread blocks may go faster than others, so they may be already done, ready to move on, but we need to make sure that all of these elements are loaded first. So we can call sync threads to do this. Okay, so the next thing we need to do is just matrix multiplication, right? And so for this, we'll go ahead and have a temporary variable, right? We'll go ahead and set int temp equal to 0 up here. And then in here, we'll do for int I is equal to, or we've already used I, j is equal to 0, j is less than dim, j plus plus, right? So now, just to clarify, right? So like I said, we're basically splitting our big matrix multiplication, our n by n matrix multiplication, to chunks of 16 by 16 matrix multiplication, right? So we'll be doing this for loop on 16 by 16 chunks, and then how many times we have to do that is determined by this outer loop, right? And so we'll say, accumulate the partial results, right? So inside of here, we will just be accumulating into temp. So temp plus equals, and now we'll be loading from shared memory now, which we've allocated in uppercase A. And so to index that, we'll just index based upon tx, ty, and then dim, right? Unlike the kind of naive version we did last time, which was based upon row, column, and the dimensions of our matrix. Because now we're working on a small one that's just in this small shared memory that we've allocated. So here, right, it'll be A of, it'll be whatever thread we are, right? So it'll be ty, and then for the A matrix, we'll stay on the same row, right? So here it'll be ty times in, or rather times dim, plus j. So we'll figure out what row we belong to, and then we'll just go along that row. And then we'll multiply this by b. This time for b, we're going to be going down the rows in our small matrix. So this time it'll be j times dim, right? And then this time, what's going to remain constant is our column, right? And so this will be tx, right? So again, you can just kind of remember this row and column stuff by thinking back to our calculations up here. If it's a column, it's going to be generally related to the x, right? So x up here for all of these, and then tx down here. And then if it's a row, it'll be related to y, right? So here's our row, right, related to y, and our row is constant there. Okay, so that's going to go ahead and do it. The only thing we have left is after this for loop, we need to call sync threads again, right? And this might be a little bit non-intuitive, but let's see why this is. Oops, get rid of the H in there. So the reason why we need this sync threads is because, so firstly we need this first sync threads to make sure that all of our memory is loaded, right? Or all of our shared memory is loaded before we start calculating values. We need the second sync threads to make sure that all the threads are done with those values in shared memory before, maybe warps that finish early loop back around and start loading new values. So we don't want to clobber values while they're still being used by other warps. So that's why we need these two sync threads here. Okay, so that's going to do it for our kernel. The only thing we have left to do, right, in this case, is to go ahead and we'll go ahead and verify the result, right? So verify the result on the CPU, right? So we'll call verify result, right? And we'll pass it A, B, C, and in, right? And then down here, if verify result doesn't fail, we'll go ahead and print out program completed successfully, right? And then, oops, I need a semicolon, return 0 at the very bottom of the program. And so now we actually have to write this verify result and include some stuff. So we'll go ahead and split, go to the very top. So what do we actually need to include? We need to include first cassert, that's what we'll use for a functional test. We'll include IOStream for our print, and then we'll use namespace standard, pollute our namespace a little bit, but that won't matter too much here. And we're just going to use that so we don't have to do standard cout down here. Okay, so now let's actually write our verification function. Right, so here, right, verify the result on the CPU. So we'll call this a void function named verify result. We'll pass an A or int A, int B, int C, and int in, right? And then we need to go ahead and go back and make that a comma. And then we need to fix these and make sure that they're all pointers, right? Because these will be the pointers to our matrices. Okay, and then we'll just do kind of the intuitive CPU matrix multiplication, which will be for int. We need a temp variable first, right? So temp, right? And then we'll do for int I is equal to 0, I is less than in I plus plus, right? Then for j is equal to 0, j, oops, less than in j plus plus, right? And then finally, oh, we made a mistake someplace. Oh, we didn't say int. There we go. And then finally, for int k is equal to 0, k is less than, not L, k is less than n, k plus plus, right? And so we can annotate this a little bit. We can say for every row, right? So I will index our row, and then for every column, and then we'll go ahead and say for every element in the row column pair, right? So that's what each of these loops does. Right, and then in here, what are we actually going to do? We're going to compute matrix multiplication for that single, or compute that single element for matrix multiplication, right, or that single output element. So we'll just accumulate in temp, right, and then outside this loop, we'll go ahead and set temp is equal to 0 for every single element, and then we'll say temp plus equals, and this will be A of I times n plus k, right? So this time the row remains constant, the column changes because we're moving across the x dimension, and then times b of this time j, or rather k times, oh no, I was right, yeah, k times n plus j, right? So this time the row changes, so k times n, and then j remains constant, so we stay in the same column. Right, so that'll accumulate into here. our result, and then we can just check our result. So we can say check each result, and so we can just call assert and make sure that whatever temp is, it should be the exact same as whatever is in C, which is coming from the GPU, right? And this will be C of I times N plus J, right? So I and J are going to be our row and column. Really, and that's really it. So let's kind of close things out by going over everything again. So for statically allocated shared memory, we tell the compiler ahead of time how much we want. So we've got this 16 by 16 here, right? And then inside of our kernel, we can do shared int a, right? And then it'll be an array. And so how big do we want it? We want it to be shmim size. We want it to be the size of our thread blocks, which happens to be 16 by 16 or 256 elements. If we wanted to do this dynamically, we would do extern shared, and then we pass it in as a kernel parameter. Then we go ahead and calculate our global row and our column. We extracted some built-in values just to simplify our code. And then we're still going to accumulate into some temporary. So we have this int temp equals 0. Then this for loop just says, I want you to move the tile across. I want you to move the tile, or the thread block is equivalent of our tile in this case. So we're going to move this thread block and compute matrix multiplication on smaller matrices, but we'll have great locality because we're accessing shared memory instead of global memory. So now we'll do it by 16 by 16 chunks of matrix multiplication, and then move these tiles over across the A matrix one at a time, and then down the B matrix one at a time, right? Or one block dimension at a time, 16 in this case. Right, so we load from A, we'll load in one element. Every thread will load in one element of that 16 by 16 matrix. Right, so a load in from our global matrix A and our global matrix B. So we still do need to access global memory, but the only difference is we access all these elements once, right, or once per thread block. We have to call this sync threads to make sure that all these threads have loaded their elements into shared memory before other threads start trying to access them. And these are other threads in the thread block. So shared memory is thread block private. Then we actually compute matrix multiplication, but on our small 16 by 16 matrix this time, just in this small for loop, right, that goes across the dimensions of the thread block, which will be 16. And then we have to make sure we call sync threads again, because we want to make sure that while other threads may be still accessing shared memory, we don't want other threads in other warps to go back around the loop and start overriding those values up here, right? And then we could do the exact same thing in our main function where we allocate memory, initialize our matrices, calculate our CTA and grid sizes, launch the kernel, synchronize to make sure that it finishes, and we verify the result. So let's go ahead and compile this, and we can go ahead and debug if we did anything wrong. So we'll do nvcc matrix mul -o, and then we can go ahead and run this, right? So it looks like we failed the assertion, so we can go back to our kernel, and let's go ahead and see if we can spot any immediate mistakes here. Okay, so it's usually a mistake that related to these calculations over here, right? So for our loading into shared memory. So here we've got, row times n, I times dim, plus tx. Okay, so that makes sense. Then over here, I times dim times n times ty times n plus column. Both of these loading into ty. And then a of ty times dim plus j. Right, does this make sense? Yes, it should, so we'll go over j elements in the submatrix. Okay, we didn't write back our result. There we go. See, simple debugging. You can usually figure this out by just tracing your code, making sure you remembered every step. So we'll write back the result to main memory, right? So right now, our value is just stored in this temporary temp, so it's not actually in main memory, right? And so we'll just do C of row times n plus column is equal to temp, right? And that should fix it. All right. Oops. It's in one G++, one in VCC. There we go. So let's test it now, right? Okay, so it's running for a good period of time. This just, most of this time is spent verifying the result, right? So the actual matrix multiplication runs in a few milliseconds. Okay, so it completed successfully. So what are the limitations of this implementation? So we did a little bit padding here, but this isn't quite right if we wanted to make it actually general. There's a number of things we'd have to make sure that we're padding. So we need to make sure that you know, when we're loading things into shared memory, we need to make sure that the threads, you know, aren't exceeding the actual dimensions of the matrix. So in fact, you know, we can actually get rid of this here, right? So we'll just do, you know, n divided by dim, and we'll just assume that we have a power of 2 matrix right here, right? In reality, what you'd want to do is make sure that, you know, for each of these iterations, you want to make sure that you're not exceeding the bounds of the matrix. As always, right, m, n, and k, if we want to make it generalized, we'd have to handle non-square matrices, so we need some other boundary checks based upon those dimensions as well. But we can also just do a quick comparison of our code, right? So let's go ahead and set this to, say, 1 to the 12, right? So a 4096 by a 4096 matrix. And we'll get rid of verify result because we've already made sure that it works. All right, and we'll call NVCC. And then we'll zoom out a little bit, right? And then we'll go back to our other matrix mul. We'll call NVCC on this as well. Let's actually open up this matrix mul real quick, and we'll make sure that they're the same size, and we'll just show the kind of the performance difference, right? Because I said this was an optimization, so it's always helpful to see, is it actually an optimization? Is it actually faster, right? You have to measure. All right, so let's recompile that. We'll do nvprof on the first one, so this is going to be our general version, right? Or not our general version, our simple version, right? Where we didn't use shared memory. About 1.62 seconds, right, for our kernel. And then we can go back to cache tiling, right? And we can do the same thing on this version, right? And we see that it's about 784 milliseconds. So it's roughly twice as fast, right? So it's roughly twice as fast because we're not having to go to main memory all that much. We're loading things once into shared memory and then accessing it from in shared memory from there. All right, so that's going to go ahead and do it for this episode. It's a basic introduction to, you know, the full process of writing something like a cache tile matrix multiplication in CUDA. As always, feel free to check out any of my stuff at github.com/coffeebeforearch. All right, so we've got all this code from this From Scratch series and also the more in-depth stuff in the CUDA programming series as well, right, where we go over matrix multiplication, vector addition, some of the CUDA libraries, optimizing things like sum reduction and convolution, and some other miscellaneous topics. But that's going to go ahead and do it for this episode. As always, I'm Nick, and hope you have a nice day.